Okay, we're back 5 hours later. Let's do 5C, which gives you the regular expression, A or B, followed by, well, concatenated with C or D, and that whole thing is being starred. Okay, so let's go. Yeah, it is kind of tedious, but there is the machine for A, which looks like this, start state for A, and I read an A, and I go to the accept state for A, and for B, I have a start state, and this is the accept state. For B, I have, let's see, well, maybe now I'll just kind of do the A or B machine. What does it look like? The A or B machine has a start state, A or B, and from that start state I lambda to the start states of these two machines. So it's pretty simple. It's possible I could have just gone right there, and maybe I'll do that for this next one. So this is B and FB, and this is an accept state. Okay, so we get something like that. That's the that's the A or B machine, and then good. And then what does the C or D machine look like? Maybe I'll just do it over here. So the C or D machine, S, C or D, start state, and we lambda to the SC goes to FC, cha, and here is FD, cha, and SD. Okay, so that was kind of annoying. So this is the A or B machine, this is the C or D machine. Of course, oh man, I'm not even really done because, or even close to done, because now I need to concatenate them. Maybe, it's getting late at night here. Maybe we need to just do this, not tediously, recursively, but now just kind of going as we go. Because what is the next thing to do? Well, if I'm going to concatenate these two machines, let's just like do this. Then, well, what is the algorithm for concatenation? You basically go to the accept states of your left machine and remove the accept state status from the accept states from this left machine, and lambda from those to the start state of the machine on the right. So this is now both, okay, following the algorithm pretty exactly, but also just intuitively, this is a machine which is going to do A or B, followed by C or D. Okay, and then the final thing to do is to star this. So to star this, what I will now do is add a new state. So I'm going to remove the start state status of this machine, of that state. I'm going to make a new state, which is, well, okay, I don't feel like labeling it. It's just going to be the new start state. And it needs to be an accept state because an empty string does match this regular expression. And, well, I'm going to just lambda transition to what was the old start state. And then what makes this actually a the sort of the rest of the star is that you're meant to be repeating this multiple times. And so if you're repeating this, sorry, I'm just going to erase this because I need to go outside of it now. If you're going to be repeating this machine multiple times, then yeah, we might only do A or B, C or D once, in which case those should be accept states, but we might have to lambda back to the beginning. And in this case, I hope I convinced you that the beginning is here. And so lambda, so we accept if the string is totally empty, we accept, and otherwise we lambda transition back to this point again to possibly run through the A or B, C or D string over and over. Okay, good. That was like totally sufficient. I can't believe I was even considering it, doing it the long way. Okay, two more big problems. I think these last ones are the hardest ones, but they're less sort of tedious and they're more sort of exciting. And here, maybe of all four algorithms, perhaps this is the one that's like needed in the sense that I can't just do this in my head, or at least you shouldn't. So for what just happened, perhaps, you know, had I been taught nothing on this subject, I could just wing it and make a pretty decent machine that matches that regular expression. Somehow that's kind of easier, I guess. But to go from a machine to a regular expression, I find hard. Okay, anyway, that's what we're about to do. So 6b, I haven't really looked at this problem in a year or more. Here's what it says. Oh, of course it's gonna give me a machine, and then it's going to tell me to turn it into a regular expression. So let's go. I don't even have this problem done anywhere on my paper. Is it definitely 6b, 6d that I assigned? That's kind of annoying. I have different things on my paper. All right. The directions. The finite automaton 6b. The finite automaton from part B. Wait, I'm just getting paranoid now that I'm doing the wrong problem. So just let me like very fast check. Yeah, 6b, 6d. Okay. 6b. The finite automaton from part B of exercise 1 of this set of exercises. Okay, so this is the same machine from a while ago. There were these 3 states, so maybe this is going to be not that hard. S0, S1, we drew this machine way back because we did do 1b. Right? My God, did I do the wrong problem again? I am going a little bit crazy. It's possible that, well, man, I swear we did this problem, which is 1b, but I now look up here and see that 1b is not one of the problems that we were supposed to do. I don't know. Anyway, I'm going to just draw this. S0, S1, S2, we're doing this now, so let's live in the moment. Anyway, what's going on with this? This is the start state. There are 2 accept states. This is an accept state, and this is an accept state. I gotta remember to write smaller. And what do we do? Oh my God, zeros and ones. I kind of like semi-refuse to use zeros and ones for this problem. So, well, yeah, I just refuse. I'm gonna convert zeros to A's and ones to B's because it gets so the alternation notation gets so confusing when matched with the zeros and ones. I can't do it. So okay. Anyway, so we're gonna go from S0 to S1. If I read an A, that's gonna be reading an A. From S0 to S2 is going to be if I read a B. From S1 to S1 is if I read an A. I'm just converting every 0 to A. I'm sorry, but I just got to do it. And from every S1 to S2 if I read a B. And finally, S2 goes to S1 if there's an A, and it goes back to itself on a B. Okay, so let me just quickly double check that. A, B. No, this is a terrible video. And A, B, and AB. Okay, good, good, good. So this is the machine. We are doing 6B, the finite automaton from part B of exercise 1 of this set of exercises. There it is. Okay, what are we doing with this thing? Here's what we're going to do with this machine. We are going to find a regular expression which is equivalent to this finite state machine. Okay, let's go. well, maybe I'll even just do my sort of phase 2 or something over here. What is phase 2? Phase 2 says, and here it's, I think it's especially crucial to do this, which is create a new state, which is create a new state, which is a start state, and a new final state, which is a single accept state, and lambda transition from the old accept states. Okay, so how am I even going to do this? Let's see. Maybe I want maybe S naught and S2 to be over here or something. Oh boy, that's just too hard. Okay, I guess I'll just do it. So here's my new start state S, and my new final state over here, and then I'm just gonna plop into the middle of that these three states. So yeah, I mean here they are, right? S naught, which is an accept state, S1 and S2. Cha, cha. Okay, and all right. Well, I have to do two things. I have to lambda from here to here. So that's the only thing that the new state is doing. It's really just there as a placeholder. This state, S naught, well, I just copy this all again. It's going here with an A, here with a B. Here, this is with an A. This from S1 to S2 if we read a B, and from S2 to S1 if it's an A. Okay, so far, oh, and from here there's also this. Okay, so I should have, for each of the three original states, I should have A, B, A, B, A, B. Okay, yeah, so for each of the three original states I have sort of everything there. So what have I really accomplished? Nothing, really. I mostly just copied this whole thing over. But the new thing I did was to add this new start state, lambdaing from that state to what was the old start state. But then also, we need a lambda transition from, because these are both accept states, we need a lambda transition from S naught and from S2, each of those to F. Okay, this was what Gossett called the preliminary step, and now what I need to do becomes more clear. I just need to delete one at a time this state, and this state. And if I can delete those three states, I'll be left with just my my start state S, my accept state F, and I'll have a regular expression describing this machine. Okay, let's go. So this is going to take 3 steps, right? So maybe I'll just do like 1, 2, and then 3 or something. So I don't know. This is maybe this is over planning, but maybe this is what I need to do. Let's go. Which state should we delete first? I have no concept of what one would be better than any other one. I shall delete S2. It seems to be causing a lot of problems right there in the middle. So here we go. Here's S. Here's S naught. And their relationship is pretty simple. And then S2 is being targeted for deletion. So here's S1. Here's F over here. And, well, that's going to be it, right? So here's, I mean, maybe I'll just do that or something. Okay. So, let's go. And maybe I need to do some colors now or something. So from S naught to S1, there's this A. From S1 to F, there are no transitions, but here there is a transition. And let's see, what else? S2 is really very busy. So without it, there's not that much going on. So I don't know whether that makes it the right thing to do first or not. I haven't decided. S naught goes to B. Yeah. So I think that's everything. Okay. Yeah. Good. Now I have to fully capture. So I'll switch colors now to red or something. I have to fully capture every function that string that state S2 had. Okay. So I have to consider every walk of length 2 that goes some state, S2, some other state. And I think there's going to be a lot of them. Alright, so first of all, I can't get from S, there are no transitions taking me from S to S2, so that's good. And there are no transitions taking me from F to S2 either. So really, I only need to consider S0, S0, and S1. And so to try to do this strategically, let's see. Also from S0, well, what are the paths? Maybe I'm overthinking this. Let's maybe just jot them somewhere. I don't know where. There's space for this. I guess just right here, or this will be it, right? What are the transitions I need to account for? Well, there's the S0, S2, S1 path. That's a legit path. There is the S0, S2F path. So S0, S2F is another option. And I think that's it, right? So from, maybe thinking about it this way, from S0 to S2, where else can I go? S0, S2, it's either just S1 or F. I can't go to S. And I can't go back, I can't do S0, S2 back to S0. Okay, so that's going to be 2. And then I guess there's just going to be 3 more, right? There's going to be from S1, 2 more. From S1 to S2 to S0, that doesn't exist. So it's really just S1, S2F, and S1, S2, S1. Okay, so what's going on here? I am considering every possible path from a state to S2 and then to another state. And honestly, because there are 4 states left over after I delete S2, there are 16 possible transitions. There are 16 possible paths that have the form, blank S2 blank, owing to the 4 states here. But really, that's kind of fake because S isn't doing anything, F isn't doing anything. So I think I got them all. I'm just pretty sure I did, right? So let's go. All right. Well, S, S2, S1. In other words, if I could previously have gone from S0 to S2 and then to S1, but now I've deleted S1, then I need to go sort of directly from S0 to S1 with I have to sort of capture this. So okay, how can I get from S0 to S1 sort of via S2? Well, I can do B and then some number of B's and then followed by an A. So I'm going to label this B star A. Because B some number of times A. Alright, so that handles S2's function with respect to getting from S0 to S1. Okay, how about S2's function with respect to getting from S0 to F? Well, going from S0 to F, I could go B, some number of B's, and then lambda. So keeping it simple, really I have this sort of new path from S0 to F, which is the new path I'm adding is really just B star. Okay, and so that takes care of that. S1, S2F. Well, now I could have gotten from, there was a path from S1 to F through S2 that went B, bunch of B's, lambda. So I'm going to have another B star from S1 to F. This is going to be B star. And finally, not to forget, that there was a path from S1 to S1 via S2. That path was, from S1, I do a B, some number of B's, and then an A. So I have to add a new sort of loop here, which is, what did I say? B, some number of B's, so B star A. And I just think I just got them all now, right? What else is there? Yeah, boom, 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 yep, boom. Basically, one way of thinking about it is that they all terminate in either S1 or F. Because those are the only paths out of S2. Okay, good. So I kind of need even more space than I thought, really, because this needs to be cleaned up, because now I have, okay, so I'm going to cram more machines in. They're going to get hopefully smaller and smaller as I go. Here's S. Here's S naught. And then I don't know what to put, what to do here. I'll just put S1 and F. And what are, hopefully that's enough space, what are the transitions? Maybe it's just not enough space. So here's S1, here's F. What are the transitions? Well, from S naught to F, the transition is going to be now labeled as B star, or lambda, because we can get just like a free pass straight from S naught there. So that's good. From S naught to S1, I shall now label it with A or B star A. Did I say this was not tedious? So 1, 2, from S1 to F, I have the same thing, I have just that, right? B star. But now from S1 to itself, I have to label that with A or B star A. Okay, so this was, I actually made this kind of a two-step process, or at least I drew two pictures, but I've only gotten rid of one state so far, which is S2. Okay, now, I don't know, let's get rid of S1, maybe? Seems like a good idea? Sure. So if I'm going to get rid of S1, now I'm just going to have S naught, and F. And okay, I mean, by this point we're basically done, right? So this is really, well, okay. So this is really kind of the last step, actually. So maybe I'll make a little bit more room. So here's S naught. Here's F, and it's going to be an accept state, and we got this. Okay, so so good. That's lambda, and now if I'm going to delete S1, then I need to fully recapture what S1's function is. But I think here it's clear that there's only one option, right? It's from S naught to S1 to F. Is the only one. So what is the? I'm gonna just do this in purple because it doesn't matter what color you're doing it in. So what is the path from S naught to F? Well, there's this path. First of all, the one that already existed. So that's going to be B star, or lambda, parenthesis around that, because that's one path from S naught to F, or the path from S naught to F via S1, which will go A or B star A. I think I need parentheses there. And yeah, this was sort of bound to happen. So that, or this followed by some number of A or B star A star, followed by B star, will get me to F. So this is pretty hard. Chance for error, extremely high. But anyway, the final thing to do is to get rid of S naught, which is just going to throw in one sort of last option, which is that the empty string should be accepted by this machine, which is clear intuitively. And so, sort of like way over here or something, I'm left with this kind of redundant machine with just a single start state and a single accept state. And the string, so the final answer for this regular expression is it's lambda, or, and then basically just all of this, right? So I need another giant parenthesis, over this entire thing. So it's like parenthesis B star or lambda, or A or B star A followed by A or B star A star B star, and there's just a whole parenthesis around that. Do I need that parenthesis? Yeah, I guess I do. There are some potential ways in which I could, well, I'll leave that there. That is certainly right. That's certainly right. Or that whole thing. Yeah. Okay. Woo! I can't say that was fun. I thought that was going to be fun, but it wasn't as much fun as I thought. And now I get to do one more of these. Let's not stop now. Let's do it. This is only like a 50% chance of this problem being right here, by the way, and I should say that you will get a totally different answer if you target your states for deletion in a different way than I targeted my states for deletion. So if you deleted your states in a different order, you'll get a different regular expression. And are those two regular expressions equivalent is a really hard question. Fortunately, shout out to Reynolds, who 2 years ago, he should really be famous for this. I was despondent that there was seemingly just no way to check whether two regular expressions were equivalent, and thinking that this was like a relatively, I don't want to say easy, but thinking that this was a relatively basic kind of thing that computer scientists would want to know, I spent endless hours Googling it, and I even contacted some like computer science major college students who were my former students and people who worked at Google, and everyone was just whining and complaining that it's like an NP hard and all that kind of stuff. It was just like, stop complaining that it's NP hard, just do the algorithm and I'll just give you small strings and like it'll be okay. It did not exist. As far as I know, there's just nowhere on the entire internet where you can just type two regular expressions and it will tell you if it was equal or not. And Reynolds 2 years ago just like found some program on the internet that someone had written, though with significant errors, and he fixed the program, and currently the only working regular expression equivalence checker anywhere other than the entire universe perhaps is somewhere up on like some website that Reynolds made. So that's pretty exciting. 6D, we do it. What is 6D? Well, I guess it's just going to give me another machine, right? And I need to turn it into a regular expression. Let's go. 6D, the finite automaton from part D of exercise 1 of this set of exercises. Oh, hello, finite automaton. I have seen you before. Because we did this problem. We did 1D, and I guess it's crazy. I should just change the homework because no one's done it yet. On this video, I definitely went over 1B. It's just a fact. Okay, anyway, looking forward. Here we go. There's this start state. There's this accept state A. There's this accept state B. And there's this C. Okay, and if I was back at Blair, I would just use up like an entire whiteboard for one of these problems. And it would just be so beautiful and satisfying. So here we just need to cram it in. C, so that makes me sad also. And then this is A, and B, and this is a B, and this. Oh yeah, so I remember this machine. This is the machine which just accepts. This is another machine I don't completely understand why it needs to be the way it is. But this accepts any string that has an A or B in it, but no C's. So do I have and 3 arrows coming out of every state? I suspect that I do. We're looking good. Okay. This problem I did actually. So it's just a mere 7 steps is all that's required. Okay, let's go. No point in whining about it now. What are we going to do? We are going to follow the algorithm like, you know, carefully, like a serious person. So that's step one. Step two is to add in a new phantom start state and accept state. Kind of don't really want to do this, but I guess I just have to. I seemingly abandoned this at some point. Hold on, give me 1 second. S naught. Maybe yeah. I think I'm just gonna. Okay. Basically, here's what it comes down to. I modified, even when I taught this topic, I modified the algorithm kind of on the fly. Because as long as there are no transitions to the start state, then I don't think I really need to create a new start state. Honestly, as long as there's only one, well, okay, so I'm not going to create a new start state. I'm just going to create a new accept state. So, okay, here's what we have. We have S, there's this A over here, there's this B over here, there's this C over here, and then there's this new state, F, which is the single accept state. And this single accept state is going to, first let me just recopy everything. So A is still just preliminary step. B, here we go to C. Oh boy. A, B, C, A, B, C, and is that good? It probably is. A, B, oh no, and I almost missed that, so that's a B. Okay, so far all I've done is to just copy the machine over again, just exactly, yeah, correctly. And now I'm going to do just this one new thing, which is to add this new state F, and I'm going to lambda transition from the states which are accept states. So we have, what we get is a lambda transition here, and a lambda transition from B to F. Alright, and now the algorithm kind of begins, which is to say we now delete states. And I am going to, oh, no, I get to do one more thing, I forgot. I get to kill any garbage state. Oh, that's so satisfying. So, I forgot about that. Any state, which is a garbage state, can just be deleted entirely. Because it just freaking didn't need to be there in the first place, basically. So I'm just going to delete all of these. I'm just going to delete that state because it has no bearing on anything at all. And now we just get here. Let me clarify that a little bit more. It's a garbage state in the sense that there were no arrows leading out of it, and therefore it was there merely to satisfy the definition of deterministic finite automaton, but by deleting it, you have a non-deterministic finite automaton, which is just exactly